Welcome everyone. My name is Bruno Herlin and I'm one of the co-chairs for this session. This session is entitled Geosynthetic Clay Liners. A couple of things to note before we start the presentation. You will have the opportunity to ask questions during this on-demand session by clicking the question button at the bottom of the video window. Your question will be sent to the presenter to answer as soon as they are available. To claim PDH credits for this session and any other educational session, you will simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the surveys for any sessions that you attend. Please note that you will need to include the verification code shown on this session to verify that you attended the session and ensure that you receive the proper credits. My co-chair for this session is Kent von Mobage. The three papers are Premature Hydration of Geosynthetic Clay Liners, Flow Swell Index as an indicator of chemical compatibility of bentonite polymer composite GCLs. And the last paper will be Implications of the Effect of Freeze-Thaw Cycles on Geosynthetic Clay Liner Performance of Potential Leakage Through Covers Over Arctic Mine Waste. And on this note, please enjoy the presentations.
Good day. Today's presentation is on premature hydration of geosynthetic clay liners. My name is Bruno Herlin. I'm with Terrafix Geosynthetics, and my co-authors are Ryan Akerman and Bill Kennedy. Ryan is my plant technician who did the testing for this paper, and Bill Kennedy is my vice president of manufacturing. And today's presentation, like I said, is on premature hydration of geosynthetic clay liners. And as someone who's worked on geosynthetic clay liners for over 20 years, this is a question that comes up from time to time. As a manufacturer, we get asked either by engineers or contractors on a project that it has rained on top of my geosynthetic clay liner, or it has snowed on top of my geosynthetic clay liner. And we have recommendations and guidelines to do in case a geosynthetic clay liner gets hydrated, fully hydrated or partially hydrated, and what to do in those instances. And there are many factors that have to go into when you're answering this question and or supplying an answer to the problem of a geosynthetic clay liner being hydrated before any cover soil is placed over it. The many factors are what type of geosynthetic clay liner was actually sent to the project, and again, what type is the application? Is it a stormwater management pond or is it a landfill? And hopefully this paper will address some of those questions and the recommendations that we provide. And really the beef of it is it's not something that is overly to be concerned about if a particular type of geosynthetic clay liner is used on a project. Now, the current guidelines for geosynthetic clay liners is that a GCL be deployed in a dry condition. There should be no presence of excessive moisture. Should not be left overnight. Now, these guidelines were written when geosynthetic clay liners were just simply bentonite sandwiched in between two textiles. They were needle punched at the time, and now most of the geosynthetic clay liners that are available on the market are needle punched. Some are needle punched with a low peel strength. Some are needle punched with a high peel strength. Some GCLs might have only two textiles. Some GCLs might have three textiles. Some GCLs might have a polypropylene coating applied to it. Some GCLs might have a geomembrane either applied to it by a gluing method, or even in some cases I've seen them needle punch, which doesn't make any sense to me. But what the basis is not every geosynthetic clay liner is made differently. Not every GCL will behave the same. And so these are factors that need to be considered in case there is a precipitation or a rain event or a snow event on top of a geosynthetic clay liner. So in this picture, everything looks great, nice dry site, everything's subgrade's perfect, nothing's wet, and hopefully all your projects are like this. Unfortunately, this is not a reality on a project. The reality in life is that there's always moisture everywhere. Doesn't matter where you are in the world, there's moisture. So it can be, you're on a job site, there's stubborn groundwater present. Is it something to be concerned about? Now, as you can see in this picture, they're putting down a geosynthetic clay liner in a stubborn groundwater condition. 6 to 9 inches of water? Go ahead, put down the geosynthetic clay liner. It's a stormwater management pond application. Do not be worried about it. Why not be worried? Because a particular type of geosynthetic clay liner that is robust, has a high peel strength, has 3 textiles in it, nothing to be concerned about. Now, I wouldn't say those comments if the project was maybe a geosynthetic clay liner that only had 2 textiles. From the 20 years that I've had, some GCLs can take the abuse on a project if there is a rain event or a snow event. Now, with everything in life, if you didn't get the right type of geosynthetic clay liner, you went with a lower grade type of geosynthetic clay liners, I wouldn't be able to make those comments. You wouldn't put down a geosynthetic clay liner in water if it had a low peel strength, or if the geosynthetic clay liner, as I said, only had 2 textiles. Now, the whole basis of this paper, like I mentioned from the get-go, not every GCL is alike. And so with every type of geosynthetic clay liner, you could literally have a different type of installation and guideline written. And you could also have different types of recommendation in case a geosynthetic clay liner does get hydrated. Now, in my last slide, it was a stormwater management pond application. In this slide, it's a landfill application. Is it cause for concern? All depends. Now, here in these applications, you're putting down a geomembrane on top of a geosynthetic clay liner. You're putting down either a high-density polyethylene or linear low-density polyethylene over a hydrated geosynthetic clay liner. As you can see in the pictures, some GCLs not hydrated, some GCLs partially hydrated. Some of the rolls are fully hydrated. And as manufacturers, every manufacturer has their guidelines written on what to do and what not to do. And it'll be discussed in later slides. Is it cause for concern? Yeah, it might be if one particular type of geosynthetic clay liner was sent to the project. And it might not be if a more robust GCL was sent to a project. Now, recommendations when a GCL gets hydrated. The past practices have been to always remove and replace the geosynthetic clay liner. Please do not do this. Please do not do this. Leave it there. There's nothing wrong with leaving a fully hydrated geosynthetic clay liner. Now, if the application is of concern, let's say in this picture, it's a tailings dam being done on the flat. If the GCL is fully hydrated and is cause for concern for the particular project engineer or the design engineer that's on the project, you'll do more harm by removing a fully hydrated GCL in a flat condition. Leave the GCL that's fully hydrated. Place down a dry sheet of geosynthetic clay liner over the fully hydrated GCL. Trust me, on this particular site, I couldn't believe it when I got there. They were actually removing the GCL that was fully hydrated, completely removing it and bringing it up on the hill. Couldn't believe it. Hot enough as it is in Latin America, there is no harm by leaving the GCL that's fully hydrated there. And if the design engineer feels that the GCL should be replaced, please leave it in place. Put a new dry sheet of geosynthetic clay liner over the existing fully hydrated GCL. Trust me, you'll do more harm to the subgrade, and you'll have to spend more time repairing maybe the subgrade if you're trying to remove a geosynthetic clay liner. As you know, geosynthetic clay liners are very heavy, and just imagine how much heavier they are when they're fully hydrated. So just a quick recap on a prehydrated GCL before there's any cover soil placement or any type of geomembrane placed over the geosynthetic clay liner. Is there cause for concern? Well, like I said, all depends on the site, depends on the project. Are you working on a pond or a landfill, or in the previous slide, if you're lining a tailings pond for a mine site, which might be a more critical condition. It all depends on the project, as I mentioned. Is the GCL been left exposed? Wet, dry conditions might have occurred. And the construction techniques being used on the site, of course, differential loading that might be over the affected area. And the whole most important factor, in my opinion, for this paper is what type of geosynthetic clay liner is actually being used on the project. There are many types of geosynthetic clay liners manufactured around the world, as I mentioned. Most GCLs will have a top fabric non-woven, but here again, how thick is the non-woven? Is it thin or is it thick? Is it a 3-ounce non-woven fabric? Is it a 6-ounce? Is it an 8-ounce? How much bentonite are you putting in between the two textiles? Are you putting in 0.6 pounds per square foot, or 0.75, or 0.8, 0.9? Some jurisdictions want you to put 1 pound per square foot of bentonite. So these are all factors that have to be looked at when a GCL gets hydrated on a project. Is it cause for concern? The basic and most important part, well, yeah, it can be cause for concern if your geosynthetic clay liner only has a woven fabric on the bottom. Or does it have a non-woven only? Or is it a scrim non-woven? And a scrim non-woven is basically where the bottom textile of a geosynthetic clay liner is a woven and a non-woven needle punched together, and that'll be the bottom fabric. Is there a coating applied to the geosynthetic clay liner? So it all depends on the type of geosynthetic clay liner that was used on the project. If the question comes up from an engineer or contractor, what do I do? My GCL is wet. It rained overnight. Is it cause for concern? Well, there are guidelines, as I mentioned. It might not be a concern if you used a particular type of GCL, and it might be a concern if you used a low-grade GCL. Well, like I said, I've been at it for 20 years with geosynthetic clay liners, and hence the question always comes up. How bad does a geosynthetic clay liner get when it's fully hydrated? Of course, it's going to be a different answer if it's partially hydrated. So in this paper, I have to make it quite clear that the samples were fully hydrated and then the peel testing was done. Samples were fully hydrated after a certain amount of time, some for 8 hours, 16 hours, some for a day, 2 days, 5 days. And after they were fully hydrated after a certain amount of time, were taken apart as per ASTM standards. And peel testing was done as per ASTM 6496 to see what kind of peel values we would get out of these samples after they were fully hydrated. So they start off, each geosynthetic clay liner starts off with an original peel strength. Then they were fully hydrated. And then we would record the peel strength after they were fully hydrated to see what kind of peel values we get. And here are the results we get. Now, these are shown as a percentage loss. So the percentage loss in the peel values, how much percentage of peel strength did we lose? The bottom line, being the red one, is a geosynthetic clay liner has a non-woven top fabric. The bottom is a scrim non-woven. That means that the bottom fabric of the GCL has a woven and a non-woven together. And if you look at the blue line, this is a type of geosynthetic clay liner that has a top non-woven fabric and the bottom being a woven fabric. So as you can see here, in a fully hydrated 8 hours, you've already lost 28 to 38%, depending on the type of geosynthetic clay liner you use. Why did I ask for this testing to be done? It's because I mentioned we have some contractors that will line something that's not critical. They'll line a stormwater management pond, let's say. They'll put 10,000 square meters out, leave it exposed. There'll be some rain event. It might be partially hydrated. Sometimes the bottom will be fully hydrated after 5 days. Not cause for concern because it's a stormwater management pond. Now, I should stress, I'm only looking at the peel values on this simple test paper. We're not looking at permeability and performances. So this is just something I've observed over the last 20 years is that scrim reinforced GCLs, the ones that have a top non-woven fabric and one that has a bottom fabric, which consists of a woven and a non-woven, hence scrim non-woven. These are more robust GCLs. They can take the abuse when there is a rain event or a snow event, and there'd be no cause for concern for performance. Like I said, stormwater management pond, not much concern. Now, if you're doing a landfill, there'll be a lot of guidance and surveillance being done on a project. So I can't see a geosynthetic clay liner being left exposed for 5 days on a landfill. Most of the guidelines is if you're going to put a geomembrane over a geosynthetic clay liner, you'll only put out so much GCL in a day that you know that you're going to be covering it up with either a geomembrane or cover soil. I just asked for the testing to be done in extreme conditions where you might have a contractor with no supervision being done at all. They'll put the GCL down and some other urgent matter might come up. They might have another project that might need attention. So they'll put the GCL down and leave. Is it cause for concern? As I said, I don't think there is if you're using a scrim reinforced GCL, a GCL that has a non-woven top and a scrim non-woven bottom fabric. So cause for concern if a GCL does get hydrated before a geomembrane or cover soil is applied? My opinion, no. But again, it all depends on the type of GCL that's being used and the type of geosynthetic clay liner that was selected on a particular project. And again, it all depends on the application that's being done. And this is what you want to see if you're putting in a geomembrane over a geosynthetic clay liner. In this picture, you can see the top geomembrane just at the top edge of the slide. And you want to see a nice monolithic looking type of geosynthetic clay liner that's nice and moist, hasn't been squeezed out or anything, sitting on top of the subgrade. This is not what you want to see out of a geosynthetic clay liner. Again here, the HDP has been cut out just at the top edge of the slide. You can see the high density polyethylene has been cut. It's hard to see. This is not what you want to see out of a geosynthetic clay liner. A geosynthetic clay liner that went through many wet, dry cycles before being installed, or went through many wet, dry cycles during deployment before the geomembrane was put on top of it, or before cover soil was put on top of it. Now, in the previous slide, GCL looked great. In this slide, the geosynthetic clay liner, not so much. Now, high profile sites, most of the time they're always dry. Why? It's because there's a lot of supervision being done on these high profile sites. This one here is a high density polyethylene being put on top of geosynthetic clay liner. Very interesting project. Like I said, high profile sites, there's a lot of supervision. The GCL will always go down dry. And of course, they're never going to put as much geosynthetic clay liner as they know they're not going to cover overnight. So if they're going to put out, 4,000 to 5,000 square meters of geosynthetic clay liner, it's because they know they're going to be covering 4,000 to 5,000 square meters of geomembrane on top of the geosynthetic clay liner. So it'll never be left exposed. But in reality, other sites like this one here, stormwater management pond being done, there's no supervision. You'll never see any engineer on a job site, just a contractor and himself or herself putting down the geosynthetic clay liner. They're putting down the GCL in wet, stubborn conditions. Wet, stubborn groundwater, as you can see here, or the subgrades not even done properly. So instead of doing a 1 foot overlap, they're going to do a 3 foot overlap on the geosynthetic clay liner. Again, is it cause for concern for a stormwater management pond with a geosynthetic clay liner being fully hydrated before cover soil being placed over it? Not at all. It isn't if a particular type of geosynthetic clay liner is used. So like I said, if you're using a geosynthetic clay liner that's screen reinforced double non-woven GCL, no cause for concern. And it might be if this contractor ended up selecting a lower grade type of GCL. Hence the basis of me asking for the testing, a simple peel test to be done at our manufacturing plant. And in the future, we'll look at different types of GCLs and test them fully hydrated and see what kind of peel strength loss we get out of it. And coming into the home stretch of this presentation, like I said from the start of the presentation, different deployment guidelines can be issued on different types of geosynthetic clay liners. Not every GCL is made alike. Every geosynthetic clay liner can literally have its own guidelines for deployment, and it could actually have its own recommendations to have in case a rain event occurs, in case a snow event occurs. Now in this picture, as you can see here, as I mentioned before, we have contractors that will put out 5,000, 10,000, 30,000 square meters of geosynthetic clay liner in one day. Leave it exposed. They know it's not going to rain overnight. But in this picture, as I'm showing right here, this is a stormwater management pond. 10,000 square meters was deployed and a rain event occurred on the weekend. And you could see, if you look really zoomed into it, you'll see some GCL that's been hydrated at the bottom of the pond. Is it cause for concern? Not at all, because this contractor ended up using a particular more robust, higher grade GCL on this stormwater management project. So deployed it on a Friday, left it exposed on the weekend. Is there anything wrong? No. Start putting the cover soil over it on a Monday. Spend it doing it all Monday. Just cover the GCL up, and at the end of the day, you'll have a geosynthetic clay liner that's holding water in a stormwater management pond in this subdivision, future subdivision. So Conclusions and comments from the testing. Well, from the testing, we saw that there is a difference between two types of geosynthetic clay liner when it's been fully hydrated, and we've done appeal testing on it. From my observations over the last 20 years, and I've mentioned this already, I know that screen reinforced double non-woven GCLs will perform and can be left exposed in terrible weather conditions over a longer period of time. I wouldn't say the same thing with a geosynthetic clay liner that only has two textiles, hence a textile that's a non-woven top fabric and a bottom woven fabric. I wouldn't leave these types of geosynthetic clay. Thank you, and stay safe and be nice to each other, everyone, until we meet next time in person.
Hello, my name is Sarah Gustitis Graham, and I'm going to be presenting on flow swell index as an indicator of hydraulic conductivity in bentonite polymer composite geosynthetic clay liners. This is research that I completed with my advisor, Craig Benson, as part of my doctoral research at University of Virginia. So to start off, I'd like to do a little bit of a review on conventional sodium bentonite geosynthetic clay liners, or GCLs for short. So GCLs can be used in the liner systems of landfills, and they can be used instead of several feet of compacted clay. And these GCLs are actually relatively thin, only about 5 to 10 millimeters, as you can see in this cross section here. And they consist of some sodium bentonite clay that's sandwiched in between two geotextiles and typically held together by needle punching, which are these fiber bundles that you see here holding everything together. And the reason that sodium bentonite GCLs work well is that when that sodium bentonite comes into contact with a leachate, the individual granules actually swell up and create these very narrow, tortuous pore paths so that you end up with a very low hydraulic conductivity barrier. So this is really great. This works really well for very neutral solutions, low ionic strength solutions. However, if you have a waste stream that has a very aggressive leachate, and aggressive might mean something with a very high pH, very low pH, perhaps something that just has very high ionic strength or a lot of multivalent ions, then what you end up with is granules not actually swelling nearly as much, that those solutions actually impact the swell. And you end up with much larger pore paths and much higher hydraulic conductivity, because you can imagine that the solution is going to pass much more quickly through a pore path like this than it would in a very narrow, tortuous pore path like this. So to combat this, bentonite polymer composites were introduced. Bentonite polymer composites are just dry mixtures of sodium bentonite, which we see here on the left, and super absorbent polymers, which we see here on the right. So these super absorbent polymers can actually hold many, many times their weight in solution. The more ubiquitous application of very similar polymers is actually in baby diapers. So for instance, if you've held a baby anytime recently, you might appreciate there's a significant lag time between that blue line appearing on the baby diaper and your lap actually getting wet. And that's because those polymers in the diaper are able to hold many, many times their weight in solution. And it's a similar concept here. And this is some visuals of some of those polymers in their hydrated form. So sometimes you might have these cross-linked polymers, which look like these individual little granules that hydrate, or you might have linear polymers where the polymer actually hydrates into this kind of consistent gel throughout that's very stretchy and can really kind of mix itself in all in one uniform gel. And so the reason that bentonite polymer composites work, the reason that they're able to maintain low hydraulic conductivity to aggressive solutions, is that this polymer actually gets into the pore space and clogs the pore space, so that even if you have some minimal swell, which is comparative to this high hydraulic conductivity situation with the sodium bentonite granules alone, if they're not swelling, then you still could have polymer in this pore space that's clogging the pore space and leading to a more narrow, tortuous pore path again and lower hydraulic conductivity. However, previous studies have shown us that this polymer can elute out of the system over time, and when that happens, then you could see much higher hydraulic conductivity, which we hypothesized was due to pore paths opening up as the polymer leaves the system. So when we set out to do this research, we really wanted to focus in on this transition. and focus in on a couple of questions specifically. First of all, how does this transition happen? And then if we understand how this transition happens, then can we screen for compatibility between bentonite polymer composite GCLs and different leachates? So we think that an index of compatibility should really represent the mechanisms that are happening that are controlling the hydraulic conductivity. So when we looked at the polymer specifically, we wanted to look at their flow stress, which represents the shear stress at which a viscoelastic gel starts to act a lot more like a liquid, a lot more viscous than it does like a solid. So that first gel that I showed, that's a gel that has a very high flow stress, very much wants to behave like a solid. That gel that I'm showing right now, that very much wants to behave like a liquid. You can see it just kind of dripping and acting very viscous like a liquid. I'll show you one more time here. That's a very solid gel. That's something with a very high flow stress, has a lot of resistance to flow. This second gel is somewhere in the middle, much lower flow stress, but still kind of rebounds, acts very elastic. And then this last gel here is just going to act completely like a liquid. So if we look at the flow stress of these different polymers, then we think that we can understand a little bit more about their propensity for elution. So in order to determine flow stress, first we had to know some of the characteristics of the polymer. Specifically, flow stress is very influenced by the moisture content of the polymer. So once we hydrate these bentonite polymer composites, we can't really separate out that polymer anymore because it likes to stick to the bentonite, likes to mix in with the bentonite. So what we developed was this bentonite polymer moisture affinity test, where we actually separated out the bentonite and the polymer, and we added solution to a filter in between and let the bentonite and polymer compete for that moisture, similar to how they would compete for the moisture if they were mixed together. But this gives us the ability to actually separate this polymer out, which you can see here, and check the moisture content without having the bentonite affecting that. So this is just a model of this test here. This is an example. So once we had some results from the bentonite polymer moisture affinity tests, we could actually determine the different moisture contents of the different gels, either as a function of polymer loading, as a function of different kinds of polymers. So these are some different polymers that we looked at in this study. Or as a function of different leachates that are used even. And so what we saw was that depending on how much polymer was in the system, what kind of leachate was used as the hydrating solution, and what the chemistry of that particular polymer was, we could get different in situ polymer moisture contents. So once we had that information, the last step was to actually find the flow stress. So there is a relationship between flow stress and moisture content. As moisture content increases, the flow stress decreases. And so this makes sense, right? Because as you add more liquid to the polymer, you would expect it to behave more and more like liquid. So you would expect a lower and lower flow stress. And that is in fact what we saw. So once we had moisture contents from these previous two steps, we were actually able to pull that moisture content, look at these relationships that we developed, and say, okay, based on this moisture content, this is the flow stress that we think this polymer should have in situ. So initially what we tried to do was just look at hydraulic conductivity as a function of flow stress to see if there was a relationship there. And what we saw honestly was, there was some delineation where if you had a really low flow stress, then you might have a higher hydraulic conductivity. But once you got past a certain point, there really wasn't a great correspondence between flow stress and hydraulic conductivity. So we went back and looked at, okay, well, swell index is a test that's traditionally used to gauge the hydraulic conductivity of bentonite. So what about, just going back to swell index? And we saw something similar where there was some pattern where if we had very high swell index, then we had lower hydraulic conductivity. But for instance, right here, for very similar swell indices, we had a wide range of hydraulic conductivities. So our new flow stress test didn't necessarily capture the hydraulic conductivity, and neither did the traditional method of swell index, which is just measuring the amount that the bentonite, and in this case, the bentonite polymer composite, is swelling in the hydrating solution. And the reason that we don't think that either of these two really capture the hydraulic conductivity is that either of these really only represents one mechanism that can control hydraulic conductivity in a bentonite polymer composite. So in a bentonite polymer composite, there's two factors here. First of all, like I mentioned earlier, that polymer can get into the pore space and can clog the pore space to create narrow tortuous flow paths. And that's one way to create those really small pore paths and to create lower hydraulic conductivity. However, you could still have your sodium bentonite granule swelling, in which case you would have the narrow tortuous pore paths as well. So what we developed was what we're calling our flow swell index, which is actually the product of the polymer flow stress and the swell index of the sodium bentonite. And this kind of captures both of those mechanisms that are happening. And what we saw when we compared hydraulic conductivity to the flow swell index was a much more clear delineation, where we had a group of low flow swell index BPCs that had high hydraulic conductivity. We had a group of high flow swell index BPCs that had lower hydraulic conductivity. And we had this relatively narrow transition zone here, where for intermediate flow swell indices, we had a range of hydraulic conductivities. And so this was very promising for us. Of course, we're continually working on expanding this data set. We would very much like to verify this with additional BPCs, additional leachates, but we think that this really does have a lot of promise as an index of hydraulic conductivity. And we think that this really could show some potential in the future because it captures the mechanisms that are happening. So a couple of other notes that I wanted to highlight while we were doing this research. This is just an example of the hydraulic conductivity of two of the samples that we saw while we were running these tests. The first here you can see had consistently low hydraulic conductivity up to about 1 pore volume of flow, and then it really jumped in hydraulic conductivity. We really saw this dramatic increase. In contrast, we had another sample, different BPC, different leachate, where the hydraulic conductivity just kind of gradually increased over time. And we think that these are both a result of polymer elution. However, this really dramatic case was something we wanted to analyze a little bit more. So we took a closer look at what was happening, especially in this situation. And what we saw, this is that permeameter, that GCL after it was broken down, removed from the permeameter. And what we saw was this very narrow pore path that's highlighted here by the pink rhodamine dye. And so that shows us that there definitely is an effective polymer elution here, where we're opening up a preferential flow path and ending up with very high hydraulic conductivity and this really dramatic transition. And we've seen that this can happen on a much slower scale as well. So these are definitely things that we want to consider when we're considering bentonite polymer composites. And this is, again, another reason why we think that the flow swell index is important, because, for instance, this sample was actually in that intermediate zone, and this one was one that eventually jumped. So we think that the relatively low flow stress and swell of that BPC led it to have an initially lower hydraulic conductivity, but eventually a much higher hydraulic conductivity. So I just discussed a lot about how polymer elution kind of plays a role into hydraulic conductivity. This is just another way to visualize that. So here we have the polymer concentration of the effluent plotted against the hydraulic conductivity. And you can see that as hydraulic conductivity increases, the amount of polymer in the effluent actually decreases. The reason that we think this is the case is, first of all, as the polymer elutes, there's less polymer remaining at higher hydraulic conductivities for the solution to contact and to dissolve that polymer. Not only that, but because at these higher hydraulic conductivities, the solution is moving through the BPC more quickly, it's not picking up as much polymer. And so you end up with a much lower polymer concentration in these effluents. However, it is important to remember that at these higher hydraulic conductivities, you're producing a lot more you're producing a lot more effluent. And so ultimately, the flux of the polymer, which is plotted here on the right, is increasing as the hydraulic conductivity increases. So these are just some more important things to note about polymer elution in BPCs. So some big takeaways from this research: we do think that flow swell index has strong potential as a mechanism for hydraulic conductivity, and that's because it really does correspond with those two primary mechanisms, the flow stress of the polymer, the elution potential of the polymer, and the swelling of the bentonite that control hydraulic conductivity. Not only that, but we do see that there are dramatic sometimes increases in hydraulic conductivity. These can sometimes occur after the equilibrium criteria prescribed in ASTM D6766 is met. So this is something that's really important to note for the future, because we really don't want to treat these just like traditional sodium bentonite GCLs. We really want to understand these, look at these as the unique products that they are. So I do want to touch on, in my last couple of minutes here, a little bit of the work that we're doing going forward. This was all some empirical evidence that I've shown you. We're looking going forward at actually being able to model how these polymers elute out of the pore space and how other properties, for example, their viscosity, can affect their movement. So these are just some preliminary models that we've run, where these blue blobs here are examples of the polymer, and the red is the permeant solution, and showing how, as we decrease the viscosity, how the polymer elutes a lot more readily out of the system. And not only looking at how the polymer elutes, but looking at how that actually changes the velocities. So for instance, this is that same model before polymer elution, where the velocity is all concentrated down this very narrow pore path. And after the elution, the velocity, the flow is all concentrated down the middle here. And you can see, based on these axes here, that this is actually 5 orders of magnitude difference between the velocities that we're seeing in these profiles. So this is a little bit of the research that we're doing going forward to further understand how we can screen for compatibility between these BPC GCLs and different leachates. Some of the key practical impacts of this research that I think are important to touch on: the more that we can understand the mechanisms that are controlling polymer elution in GCLs, the better we can hopefully improve design going forward, the better that we can work with manufacturers and really get some great products to incorporate into landfill liners. If we can use these kinds of methods of looking at the elution to predict the long-term performance and the service life of BPC GCLs, then hopefully we can mitigate risks to human and environmental health and safety. Not only that, but if we're able to have these great screening methods and we can look at the appropriate products for the leachates that we're designing for, then we can reduce costs. And then finally, I introduced at least one new test that we developed as part of this research in this presentation today. And the more that we can develop these test methods that are specific to bentonite polymer composites, the more we can accelerate research and really learn more about these. So with that, I'd like to thank you very much for taking the time to watch my presentation. I know since this isn't live, you can't hit me with questions right off the bat, but I would welcome any questions to the email listed here. And again, thank you so much for your interest and your time.
Hello everyone, my name is Farah Barakat. I am a PhD student at Queen's University, working under the supervision of Dr. Carrie Rowe. And today, I will be talking about the effect of freeze and thaw cycles on a geosynthetic clay liner performance and leakage through covers over Arctic mine waste. Composite liners can act as a component of a barrier system to prevent contamination in several different areas, such as lining the base of a landfill or acting as a cover in mine waste areas or facilities. A composite liner typically consists of a geomembrane that lays directly on top of a geosynthetic clay liner. These 2 layers usually have imperfections, So, when we lay them on top of each other, in most of the times, they are never in perfect direct contact. So, when fluid is present between these two layers, it has the capacity to move laterally. A parameter called the interface transmissivity, which we typically denote using the Greek letter theta, is introduced to represent the resistance to fluid flow that exists between these two layers. If the geomembrane is left uncovered and exposed to sunlight on the field, it will expand when heated and develop wrinkles. This happens because polyethylene has a high coefficient of thermal expansion. Once the cover soil is placed and construction operation starts being performed on top of the liner, holes will develop in the geomembrane, especially in these wrinkles. This happens even when good quality assurance is present on site. A holed wrinkle will act as a conduit for storing and distributing fluids over a much larger area than would occur if the hole were in direct contact with the GCL. And flow will develop beneath the wrinkle itself and along a certain wetted distance beyond the edge of the wrinkle. This happens because lateral flow will exist between the geomembrane and GCL layers. As shown in the equations, the wetted distance A0 depends on the interface transmissivity and the hydraulic conductivity of the geosynthetic clay liner. In addition, this distance is a function of the amount of leakage that will develop beneath the wrinkle. Once the wrinkles form, the GCL section beneath the holed wrinkle is no longer confined. The hydraulic conductivity of the GCL is dependent on the stress applied on it. Thus, the hydraulic conductivity along the area beneath the wrinkle will generally be higher than the remaining GCL. We will differentiate these two conductivities by calling the one beneath the wrinkle KB and that where the geomembrane is in contact with the GCL, Ka. Mine waste covers are typically subjected to low applied stresses that range between 10 and 25 kilopascal. The use of composite liners for mine waste covers under Arctic conditions usually results in the formation of ice lenses along the geomembrane GCL interface or between the geotextile and sodium bentonite layers of the geosynthetic clay liner, like the ones you can see in the picture on this slide. Depending on the weather conditions and thermal gradients between the top and bottom of the composite liner and the moisture content of the GCL, these lenses experience different number of freeze and thaw cycles over time. Jabin tested the impact of the number of freeze and thaw cycles on the interface transmissivity of the geomembrane GCL interface by performing transmissivity tests on composite liners that have been subjected to 5 and 16 freeze and thaw cycles in traditional closed system conditions in the lab. These tests were permeated with GS solution. Under 10 kPa overburden stress, Jabin got the following results shown in the table, where, as you can see, the interface transmissivity for a composite liner subjected to 16 freeze and thaw cycles is more than 18 times higher than that subjected to 5 cycles. To check if overburden stress has a significant impact, Jabin did the same two tests again under a 15 kPa overburden stress. and the results showed that the interface transmissivities obtained are much lower in this case. The composite liner experiencing 16 freeze and thaw cycles is now only about 2 times higher than the one that was subjected to 5 freeze and thaw cycles. Additional tests were performed by Jabin to compare the transmissivity values that can be obtained using composite liners subjected to 5 freeze and thaw cycles for different types of test setups. One using traditional closed system conditions and another using open system conditions. Open system conditions are set up to represent field conditions. So, we expect that the transmissivity results obtained from the composite liners used in this system to be more representative of field conditions than traditional methods of freeze-thaw sample preparation. In this setup, the GCL and composite liner are directly placed on the subgrade and allowed to hydrate from the soil beneath it, and the GCL remains sandwiched between the geomembrane and subgrade throughout its initial hydration and while being subjected to freeze and thaw cycles. Under an applied load of 10 kPa, the results in the table show that there is a large difference in the interface transmissivity obtained from traditional and open system tests. As we increase the applied load on the composite liner to 15 and even 20 kPa, the difference in the results from the two methods decreases and becomes less significant. So, to show how the number of freeze and thaw cycles, applied load, and type of test performed and their impact on transmissivity can influence the wetted distance and leakage that occurs beneath wrinkles, we considered 3 base cases of 1 hectare sized mine tailings consisting of a composite liner laid on top of a foundation layer with 1 whole wrinkle per hectare. The only difference between the 3 cases was the overburden stresses applied on the composite liner. The stresses considered were 10, 15, and 20 kPa, and the GCL used was assumed to have a Ka value of 6 times 10 to the minus 11 meters per second and a Kb of 6 times 10 to the minus 10 meters per second. We started by analyzing the impact of the number of freeze and thaw cycles on the leakage that occurs through hole wrinkles. This was done by performing calculations using the interface transmissivities that Jabin obtained for composite liners subjected to 5 and 16 freeze-thaw cycles. Using the conditions of the base case and the 10 kPa applied stress on the cover, we obtained the results shown in the table, where the leakage obtained for a composite liner subjected to 16 freeze-thaw cycles is nearly 4 times greater than that obtained for a liner subjected to 5 freeze and thaw cycles. When we increased the applied stress to 15 kPa and we estimated the leakage again for the 2 different freeze and thaw cycles we analyzed under 10 kPa, we still obtained larger leakage for the case with 16 freeze and thaw cycles. But the difference between the two is much less significant, and the leakage obtained for a liner subjected to 16 cycles is only 20% higher in magnitude compared to the liner subjected to 5 freeze and thaw cycles. Since the type of test performed in the lab to obtain the transmissivity proved to have an impact on the interface transmissivity results, These transmissivities were used to analyze if they would result in a large impact on the amount of leakage that would be calculated for the different cases. Under a 10 kPa overburden stress, the wetted distance and leakage obtained from the interface transmissivity listed for the composite liner that was subjected to open system conditions was more than 13 times and 9 times higher than those obtained using the transmissivity listed for the test that used a composite liner that was subjected to closed system test conditions for the same number of freeze and thaw cycles. The wetted distance and flow calculation results for the composite liner subjected to open system conditions under 15 kPa overburden stress were approximately 85% and 30% higher than those obtained under closed system conditions. While those under a 20 kPa overburden stress were 2 times and nearly 25% higher than those obtained under closed system conditions, respectively. The final table shows that performing freeze-thaw in an open system gives the more realistic but higher calculated flows. Of the cases considered, the difference in the leakage results obtained under the two system setups was maximum for 10 kPa overburden stresses and decreased significantly as the overburden stress increased to 15 and 20 kPa. In conclusion, there is a substantial difference in the interface transmissivity of a composite liner that is subjected to different numbers of freeze and thaw cycles, especially under low loads. The difference in theta results in a significant difference in the leakage calculated beneath hold wrinkles. Under low loads, choosing the correct type of test setup is critical and can have a major impact when estimating the transmissivity and calculating leakage. The chosen thickness of the cover material is extremely important as it has a significant impact on the leakage developed beneath wrinkles. Thank you.